everyone, I am Faranjum from Sri Venkateshwara College of Engineering, Bangalore. The topic for today's presentation is Lexical Analysis in Compiler from the course Automata Theory and Compiler Design. First, we will see what is a compiler. A compiler is a software program that converts the high-level source code written in a programming language into low-level machine code that can be executed by the computer hardware. The process of converting the source code into machine code involves several phases or stages which are collectively known as the phases of a compiler. The typical phases of a compiler are lexical analysis, syntax analysis, semantic analysis, intermediate code generation, optimization, and code generation. Now we will see the first phase of the compiler, lexical analysis. It is also called as a scanner. It takes the output of the preprocessor, which performs file inclusion and macro expansion as the input, which is in a pure high-level language. It reads the characters from the source program and groups them into lexemes. Each lexeme corresponds to a token. Tokens are defined by regular expressions which are understood by the lexical analyzer. It also removes lexical errors, comments, and white spaces. Role of a lexical analyzer. The lexical analysis is the first phase of the compiler, where a lexical analyzer operates as an interface between the source code and the rest of the phases of a compiler. It reads the input characters of the source program, groups them into lexemes, and produces a sequence of tokens for each lexeme. The tokens are sent to the parser for a syntax analysis. The lexical analyzer also interacts with the symbol table, like passing tokens to the parser. Whenever a token is discovered, the lexical analyzer returns a representation for the token to the parser. If the token is a simple construct including parenthesis, comma, or a colon, then it returns an integer program. If the token is a more complex item, including an identifier or another token with a value, the value is also passed to the parser. The lexical analyzer also handles issues including stripping out the comments and white spaces. The correlating error messages that are generated by the compiler during lexical analyzer with the source program. For example, it can maintain track of all new line characters so that it can relate an ambiguous statement line number with each error message. It can be implementing the expansion of macros in the case of macro preprocessors are used in the source program. Advantages of a lexical analyzer. It is efficient, it is flexible, it helps in error detection and code optimization. The disadvantages are complexity, limited error detection, increased code size, and reduced flexibility. Input buffering. The lexical analyzer scans the input from left to right, one character at a time. It uses two pointers, begin pointer BP and forward pointer FP, to keep track of the pointer of the input scanned. Input buffering is an important concept in compiler design that refers to the way in which the compiler reads input from the source code. In many cases, the compiler reads inputs one character at a time, which can be a slow and inefficient process. Input buffering is a technique that allows the compiler to read input in larger chunks, which can improve performance and reduce overhead. The basic idea behind input buffering is to read a block of input from the source code into a buffer and then process that buffer before reading the next block. The size of the buffer can vary depending on the specific needs of the compiler and the characteristics of the source code being compiled. For example, from the figure, the initial configuration. Initially, both the pointers point to the first character of the input string as shown above. The forward pointer moves ahead to search for end of lexeme. As soon as a blank space is encountered, it indicates the end of lexeme. In the above example, as soon as the pointer FP encounters a blank space, the lexeme int is identified. The forward pointer FP will be moved ahead at white space. When FP encounters white space, it ignores and moves ahead. But then the begin pointer BP and the forward pointer FP are set at the next token. The input character is thus read from the secondary storage, but reading in this way from secondary storage is costly. Hence, buffering technique is used. A block of data is first read into a buffer and then second by lexical analyzer. Specification of tokens. There are three specifications of tokens: strings, languages, regular expressions. Strings, an alphabet or character class, is a finite set of symbols. A string over an alphabet is a finite sequence of symbols drawn from that alphabet. The operations that can be performed on the string are prefix of string, suffix of string, proper prefix of string, proper suffix of string, substring of string, proper substring of string, subsequence of string, and concatenation of string. Language. A language is any countable set of strings over some fixed alphabet. Operations on language are union, concatenation, clean closure, positive closure. Regular expression. A regular expression is a sequence of symbols used to specify lexeme patterns. A regular expression is helpful in describing the languages that can be built using operators such as union, concatenation, and closure over the symbols. A regular expression R that denotes a language is built recursively over the smaller regular expression. Regular set. A language that can be defined by a regular expression is called a regular set. Regular definition. Giving names to regular expressions is referred to as regular definitions. Recognition of tokens. Recognition of tokens in compiler design is a crucial step. It breaks down the source code into understandable parts like words and symbols. This helps the compiler understand the code's structure and meaning. Tokens obtained during lexical analysis are recognized by finite automata. Finite automata is a simple idealized machine that can be used to recognize patterns within input taken from a character set or alphabet denoted as C. The primary task of a finite automata is to accept or reject an input based on whether the defined pattern occurs within the input. There are two notations for representing finite automata. They are transition table, transition diagram. Transition table. It is a tabular representation that lists all possible transitions for each state and input symbol combination. Transition diagram. It is a directed labeled graph consisting of nodes and edges. Nodes represent states while edges represent state transitions. Components of transition diagram. One state is labeled the start state. It is the initial state of transition diagram where control resides, where we begin to recognize a token. Positions in a transition diagram are drawn as circles and are called states. The states are connected by arrows called edges. Labels on edges are indicating the input characters. 0 or more final states or accepting states are represented by double circle in which the token has been found. Issues in the design of code generator. In the code generation phase, various issues can arise. First one, input to the code generator. The input to the code generator contains the intermediate representation of the source program and the information of the symbol table. The source program is produced by the front end. We assume front end produces low-level intermediate representation, that is, values of names in it can be directly manipulated by the machine instructions. The code generation phase needs complete error-free intermediate code as an input requires. The next is a target program. The target program is the output of the code generator. The output can be assembly language. It allows subprogram to be separately compiled. Relocatable machine language. It makes the process of code generation easier. Absolute machine language. It can be placed in fixed locations in memories and executed immediately. The next issue is memory management. During the code generation process, the symbol table entries have to be mapped to actual P addresses and levels have to be mapped to instruction addresses. Mapping name in the source program to address of data is cooperating done by the front end and code generator. Local variables are stack allocations in the activation record, while global variables are in static area. Instruction selection is the next issue. Nature of instruction set of the target machine should be complete and uniform. When you consider the efficiency of target machine, then the instruction speed and machine idioms are important factors. The quality of the generated code can be determined by its speed and size. Register allocation. Register can be accessed faster than memory. The instructions involving operands in register are shorter and faster than those involving in memory operand. The following subproblems arise when we use registers. Register allocation. In register allocation, we select the set of variables that will reside in register. Register assignment. In register assignment, we pick the register that contains variable. Certain machine requires even odd pairs of registers for some operands and results. Evaluation order. The efficiency of the target code can be affected by the orders in which the computations are performed. Some computation orders need fewer registers to hold results of intermediate than others. Thank you for watching the video.